In the last video, we introduced the basic quantities of rotational kinematics: angular displacement, angular velocity, and angular acceleration. In this video, we will develop some useful relationships between them. At this point in linear kinematics, we created a set of relationships between the variables that apply when acceleration is constant. These are Newton's Toolbox Equations. Now, using the linear Toolbox Equations as a model, let's examine the rotational Toolbox Equations. The first linear Toolbox equation states acceleration times time equals final velocity minus initial velocity. The rotational equivalent says angular acceleration times time equals final angular velocity minus initial angular velocity. The structure of the equations is exactly the same, and this makes sense because if you take every term in the rotational equation and multiply by the radius, you get the linear equation. The second rotational toolbox equation states that the angle swept out by a rotating object equals its initial angular velocity times time plus half angular acceleration times time squared. Again, very similar in structure to its linear counterpart. The third one states that angular displacement over time equals average angular velocity. And the fourth one states that the difference between the squares of the velocities equals 2 times the angular acceleration times the angular displacement. These then are Newton's Toolbox Equations for rotation. As we can see, the rotational forms are structurally identical to the linear forms, but with some new variables in play. Just like the linear Toolbox Equations, each rotational equation uses a different combination of the kinematics variables. Now, let's try these out. Consider this puzzle. A record player is spinning when it is switched between two settings. It accelerates at 0.4 radians per second squared and reaches a final angular velocity of 15 radians per second in 7 seconds. What was its initial angular velocity, and what was its angular displacement as it accelerated? In this question, we have a record, and this record is going to change its angular velocity. I'm first going to draw the axes. So there's x and y, and there's x and y in photo 2. Just for the sake of clarity, I'm going to draw a marker over here. And I'll draw it over here as well, just to show that this thing has rotated. Now, the final velocity of this record is 15 radians per second. We know that 7 seconds elapsed between these two photos. We also know that the acceleration, the angular acceleration, was 0.4 radians per second squared. The time was 7 seconds. And we are being asked to find the initial velocity and the displacement of this marker, basically. So let's start with the initial velocity. We know the final velocity, the acceleration, and the time. So we can easily solve for the initial velocity using Toolbox Equation number 1 in rotational form, which says angular acceleration times time is equal to final angular velocity minus initial angular velocity. So that's going to work out to 0.4
times 7 is equal to final 15 minus omega initial, which is as yet unknown. Piece of cake. 0.4 times 7 gives us 2.8. And now all we need to do is add the initial to both sides and to subtract 2.8 from both sides. So initial equals 15 minus 2.8, which is going to be equal to 12.2 radians per second. So this was the initial velocity of the marker over here in angular terms. This was the initial angular velocity, the initial rotational velocity of this marker. And then over the course of 7 seconds, it sped up to 15. The other part of this question was asking what is the displacement of this marker as it travels around the circle, as this acceleration occurs. Now, I'm going to use Toolbox equation number 2 in rotational form to solve this one. Here is how we will do it. Toolbox equation number 2 says that the angular displacement, delta theta, is equal to the initial angular velocity, that is omega initial, times time, plus 1/2 times the angular acceleration, alpha, times time squared. So that's going to be equal to initial, 12.2, times time, 7, plus 1/2 times acceleration, 0.4, times time squared, which is 7 squared. So let's start simplifying all of this. 12.2 times 7 is 85.4. Plus half times 0.4 times 7 squared. Half times 0.4 times 7 squared. That's 9.8, coincidentally enough. So 85.4 plus 9.8 gives us 95.2. So this is the angular displacement of that marker that I have. As this disk increases its velocity from 12.2 to 15 radians per second over the course of 7 seconds, the total angular displacement of this marker as it travels around the circle is 95.2 radians.
Sometimes in a rotational puzzle, we will be given quantities in linear terms. We need to convert these into rotational terms before we can solve the puzzle. Consider this puzzle. A pulley wheel has a radius of 0.1 meters. A bucket hoisted over it descends 15 meters in 8 seconds, starting from rest. What is the angular acceleration of the wheel, and what is its angular velocity when the bucket hits the water?
In this question, we have a pulley wheel and we have a bucket which is being lowered from it. The bucket is overall going to get lowered by 15 meters. But we are really focusing on the motion of the pulley wheel. So photo 1 is going to correspond to the peak height of the bucket, and photo 2 is going to correspond to the 15 meters that it descends just as it hits the surface of the water. I'm going to draw my axes on the pulley wheel like this. Now, we were told certain pieces of information. We were told that the initial velocity of the pulley wheel was 0. We were also told that the time that elapses between the two photos is 8 seconds. We were finally told, well, not finally, but we were told that the distance that the bucket falls is 15 meters, and we were told that the radius of the pulley wheel was 0.1. I'm going to write that as r equals 0.1 meters for the pulley wheel. So given all of this information, we are being asked to find the final velocity of the pulley wheel just as the bucket hits the surface of the water, and the angular acceleration of this pulley wheel. So let's go ahead and let's start this. Now, one thing that you'll notice is that at the moment we only have two pieces of information. We know the initial velocity and we know the time. That's not sufficient to solve any of the toolbox equations. But we were told one other thing. We were told that the bucket is going to descend by 15 meters. And if that's the case, that means that the rim of the pulley wheel must also have rotated by 15 meters. So that means that if I had a spot on the rim, something like this over here, this spot must have traversed a total distance of 15 meters. And so, because we know what its radius is, we can use this relationship that the displacement of the spot over here must be equal to the displacement of the bucket, since the two of them travel the same distance, is equal to its angular displacement cross the radius of the wheel. So let's go ahead and solve for this. The bucket descended by 15 meters, which means that the wheel must have rotated, the rim of the wheel must have rotated by 15 meters, is equal to delta theta, which is as yet unknown, times a radius of 0.1. So now all we have to do is we have to take 15 divided by 0.1. So delta theta is equal to 15 over 0.1 is equal to 150 radians. So this is the third piece of information that we needed in order to solve for the motion of this wheel. So let's go ahead and solve for it. The first thing we would like to find is the final velocity of the wheel. We know the angular displacement, we know the initial velocity, and we know the time. Toolbox equation number 3 will serve us very nicely for this one. So toolbox equation number 3 says the angular displacement divided by the time is equal to initial angular velocity plus final angular velocity divided by 2. So, angular displacement, 150, divided by a time, 8 seconds, is equal to initial, 0, plus omega final, divided by 2. Let's go ahead and solve for this. 150 divided by 8 gives us 18.75. If I were then to double it, that would give us 37.5. So, simplifying all of this, we get that, I'm going to write it over here. I don't like to, but I'm going to. Omega final divided by 2 is equal to 18.75. So that means that omega final must be twice that, which is 37.5 radians per second. So So this then is the final velocity of the wheel as it rotates. Now the other thing that we were being asked to find was the angular acceleration of the wheel. Since we have not yet seen the use of toolbox equation number 4, I'm going to use that over here. So this is going to read something like this. The toolbox equation number 4 says that omega final squared minus omega initial squared is equal to 2 times alpha times delta theta. So omega final, that's 37.5 squared minus omega initial 0 squared equals 2 times the angular acceleration, which is unknown, times delta theta, which is 150. 0 squared obviously is 0. 37.5 squared is 1406.25. 1406.25 is equal to 2 times 150 is 300 times alpha. So now, just divide both sides by 300, and we get 4.69. .69 radians per second squared. That is the acceleration, the angular acceleration of this disk. Every second, it gains 4.69 radians per second of angular velocity.
In this video, we explored Newton's toolbox equations for rotation. In the next video, we will move on to forces in rotation.